Hey there, space explorers. Ever heard of like a cosmic event that's so bright it briefly outshines entire galaxies?
Whoa.
Yeah, we're talking about gamma ray bursts. These like sudden flashes of intense energy
Yeah.
that leave scientists baffled and like completely in awe.
Yeah, they're really
They're
incredible.
like the universe's own flashbulbs going off billions of light years away
Yeah,
and leaving behind a trail of mysteries.
that's a great way to put it.
So today we're going to try to unravel those mysteries and discover what makes these gamma ray bursts so fascinating.
Sounds good. I'm excited.
Welcome to Cosmos in a Pod, your space and astronomy series. So what exactly are these gamma ray bursts?
Well, think of them as like the most powerful explosions in the universe.
Wow,
Bursts of gamma radiation so intense they can be seen clear across the cosmos.
that's mind-blowing. How long do these bursts last?
Well, it depends.
Okay.
We categorize them into long, short, and ultra-long bursts.
Okay.
Some are over in a blink mere milliseconds, while others can blaze for hours.
Okay, so what creates these different kinds of bursts? Are they all caused by the same thing?
That's where it gets really interesting.
Okay.
They actually have different cosmic origins.
Okay.
Let's start with the long gamma ray bursts.
Okay.
Imagine a star, much bigger than our sun, maybe 20 times bigger, running out of fuel.
Okay.
Its core collapses, imploding into a black hole, and boom, that's your long gamma ray burst.
So it's like a spectacular supernova, but even more dramatic.
Exactly, and during this dramatic collapse, incredibly powerful jets of particles shoot out, traveling at nearly the speed of light.
Wow.
These jets burst through the star's outer layers and release those intense gamma rays we detect.
So it's a black hole birth announcement on a grand cosmic scale.
Precisely. Now, short gamma ray bursts are a different beast altogether.
Okay.
We believe those happen when two of the densest objects in the universe decide to tango.
Oh, okay.
Two neutron stars, or a neutron star and a black hole,
Mm-hmm.
locked in a gravitational spiral.
Oh, wow. So like a deadly cosmic dance.
Exactly. They spiral closer and closer, losing energy through gravitational waves,
Right.
those ripples in space-time, until, bam, they collide, and you get your short gamma ray burst.
Plus, a brand new black hole and even more gravitational waves spreading out.
That's right.
Wow.
Now, the ultra-long bursts, those lasting for hours, they're still a bit of an enigma.
Okay.
There are a few theories floating around.
Like what?
Well, some scientists suspect they might be tied to the death of truly gargantuan stars, even bigger than the ones causing long bursts.
So an even more epic explosion.
Potentially, yes.
Wow.
Another intriguing idea involves magnetars.
Okay.
These are neutron stars, already incredibly dense, but with magnetic fields trillions of times stronger than Earth's.
Wow,
Imagine the energy released when those magnetic fields shift.
that sounds intense. Could those shifts trigger gamma ray bursts?
Possibly. There's still a lot we don't know about these ultra-long events.
Okay, so we've got exploding stars, colliding neutron stars, and supermagnetic neutron stars.
Yeah.
Are there any other theories out there, even if they're a bit more out there?
Well, there's always the white hole theory.
Okay.
Some scientists speculate that gamma ray bursts might be connected to white holes,
Oh, okay.
the theoretical opposites of black holes, where matter and energy gush out instead of being sucked in.
Oh, interesting.
Yeah.
So instead of a black hole birth announcement, it's like a white hole's I'm here signal.
Exactly.
Okay.
It's a fascinating idea, but remember, white holes are still theoretical.
Right.
We haven't actually observed one yet.
So we've talked about what causes these bursts, but how do they actually work? How is all that energy released so suddenly?
That's where things get really mind-bending.
Okay.
Imagine a beam of superheated matter called plasma shooting out from the source of the burst at almost the speed of light.
Almost the speed of light. That's hard to even grasp.
It is. These beams are called relativistic jets, and they're incredibly focused like cosmic lasers.
And these jets are what create the gamma rays.
Exactly.
Wow.
It's a complex process involving high-energy particles interacting with magnetic fields and photons.
Okay.
Think of it like a cosmic particle accelerator.
Okay, I'm trying to picture that. A cosmic accelerator shooting out these incredible jets of energy, but what happens after the initial burst? Is that it? Lights out?
Not quite. There's an encore, if you will, called the afterglow.
Track.
It's like the fading embers of a fire, but instead of heat, we see lower energy radiation, X-rays, visible light, even radio waves.
So it's like a cosmic echo of the initial explosion.
You could say that.
Yeah.
And By studying this afterglow, we can learn a lot about the environment around the burst, what kind of star exploded, or the properties of the objects that collided. It
Okay.
even helps us figure out how far away the burst occurred.
So the afterglow is like a cosmic fingerprint, giving us clues about the event itself and its location.
Precisely. And it can last for days, weeks, even months, giving astronomers plenty of time to study it.
This is incredible.
Yeah.
But wait, how do we even detect these gamma ray bursts happening billions of light years away? It's not like we can just point a telescope and see them live.
That's right, it's not that
Yeah.
simple.
Yeah.
Gamma rays are very high energy, and they don't make it through Earth's atmosphere.
Right.
To catch them, we need to have our eyes in space.
So we're talking telescopes in orbit.
Exactly. Satellites like the Swift Observatory, the Fermi Gamma Ray Space Telescope,
Okay.
they're constantly scanning the sky, watching for these bursts.
They're like our cosmic watchdogs, always on alert.
A great way to put it. These satellites can detect the bursts, pinpoint their location, and even analyze the gamma ray emissions. They're
Right.
giving us a front row seat to these cosmic explosions.
But isn't it just space telescopes doing the work? Don't we use Earth-based telescopes too?
Absolutely.
Wow.
Once a space telescope detects a burst, it sends out an alert, and then ground-based telescopes all over the world swing into action.
Oh, wow.
It's like a global relay race with everyone scrambling to observe the afterglow.
And by combining observations from space and Earth, we get a much clearer picture of what happened.
Exactly. It's a true team effort.
Yeah.
And we can't forget about the newest players in the game, gravitational wave detectors like LIGO and Virgo.
Oh, right. Those are the ones that detect ripples in space-time, right. What do they have to do with gamma ray bursts?
Well, remember how we talked about short bursts being caused by neutron-star collisions?
Right.
Those collisions also release gravitational waves?
So we can actually hear the collision that caused the burst.
In a way, yes.
Wow.
When LIGO and Virgo detect these waves, and at the same time a gamma ray burst is observed, well, it's like getting confirmation from two different senses.
Right.
It reinforces our understanding of what causes those bursts and gives us incredible insights into the physics of neutron-star mergers.
It's like witnessing a cosmic collision from two completely different perspectives.
Yeah.
This is absolutely fascinating. We've talked about what causes these gamma ray bursts and how we detect them, but what do they actually tell us about the universe? What's the bigger picture here?
Well, for one, they act like windows into extreme physics.
Okay.
We're talking matter moving at nearly the speed of light, incredibly intense magnetic fields, the birth of black holes, all happening in environments we can't even dream of replicating here on Earth.
So they're like natural laboratories letting us observe physics at its most extreme.
Exactly. But they also teach us a lot about the life and death of stars, especially those massive ones.
Right.
Long gamma ray bursts in particular are linked to their dramatic deaths.
So by studying these bursts, we can learn about the entire life cycle of these stars.
Precisely.
Yeah.
And when those massive stars explode, they don't just disappear.
Yeah.
They seed the cosmos with heavy elements, the building blocks of planets, and ultimately life itself.
It's incredible to think that we might be made of stardust forged in these distant explosions.
It is. And there's another amazing thing about gamma ray burst.
What's that?
They're so bright, they act like cosmic lighthouses, helping us see across vast distances and learn about the early universe.
Cosmic lighthouses. How does that work?
Think of it this way. Because they're so bright, we can see them from billions of light years away.
Right.
By measuring how much their light has stretched what we call redshift, we can figure out how far away they are and how fast the universe was expanding back then.
So they're like cosmic yardsticks, helping us measure the vastness of space and time.
Exactly. And as we've already touched on, the study of short gamma ray bursts combined with those gravitational wave detections is revolutionizing what we call multi-messenger astronomy.
Right, combining different ways of observing the same event to get a complete picture.
Yes. This approach is giving us a deeper understanding of the universe than ever before.
I'm completely in awe of these cosmic events and what they can teach us.
I am too.
Are there any particular gamma ray bursts that stand out? Ones that have really captured the attention of scientists?
Oh, definitely. There are a few that have become almost legendary in the world of astronomy.
Okay.
One that comes to mind is GRB 080319b, which earned the nickname the Naked Eye Burst.
The naked eye burst. That sounds intense.
It was. This burst was so incredibly bright that for about 30 seconds you could actually see it with the naked eye here on Earth.
Wait, people could have just looked up and seen this cosmic explosion happening billions of light years away.
If they were looking at just the right spot in the sky at the right time, yes. Remember, this burst originated a staggering 7.5 billion light years away.
That's just mind-blowing. It must have been unbelievably powerful to be visible from that distance.
It was a truly remarkable event, a testament to the sheer power of these cosmic explosions.
Wow. Are there any other notable gamma-ray bursts that come to mind?
Absolutely. Another significant one is GRB 12108 Cine.
Okay.
This one holds a special place in astronomy history because it was the first gamma-ray burst directly linked to a gravitational wave event.
So we actually detected those ripples in space-time caused by the burst.
We did, and it confirmed what scientists had long suspected, that short gamma-ray bursts are indeed caused by the merger of neutron star.
What an incredible confirmation. It must have been a monumental moment for the field.
It was.
Yeah.
It marked the beginning of a new era for multi-messenger astronomy, where we can combine observations of light and gravity to understand these events like never before.
It's amazing how we're constantly finding new ways to see the universe.
It is.
But you mentioned earlier that some gamma-ray bursts can offer a glimpse into the early universe.
Yeah.
Is there a particular one that stands out in that regard?
Yes, there is.
Okay.
GRB 090423.
Okay.
This one is one of the most distant gamma-ray bursts ever detected.
How far away are we talking?
Prepare to be amazed, it originated over 13 billion years ago.
That means we're seeing light that's been traveling for almost the entire age of the universe.
That's right.
Wow.
When we observe GRB 090423, we're essentially looking back in time, witnessing a cataclysmic event that took place when the universe was just a baby.
It's like having a time machine, letting us peer into the universe's distant past.
Precisely. And these distant gamma-ray bursts are incredibly valuable because they provide clues about the conditions in that early universe. The chemical makeup, the rate of star formation, even the properties of the very first stars and galaxies.
So these bursts are like cosmic fossils, preserving information about the universe's infancy.
That's a great analogy. They offer us a unique window into a period of cosmic history that's incredibly difficult to study otherwise.
It's mind-boggling to think that we can actually observe these events that happened billions of years ago, events that played a crucial role in shaping the universe as we know it.
It really is remarkable.
Yeah.
And as our telescopes become even more powerful, we can expect to discover even more distant gamma-ray bursts, pushing back the boundaries of our cosmic horizon and peering even further back in time.
This is all so fascinating. Gamma-ray bursts are truly incredible tools for understanding the universe.
They are, and they allow us to tackle some of the most fundamental questions about the universe itself.
Like what?
Well, we can use them to test Einstein's theory of general relativity in environments with incredibly strong gravity.
Right, that's the theory that explains gravity as the curvature of space-time, right?
Exactly. And gamma-ray bursts, particularly those associated with merging neutron stars, offer us natural laboratories to see how this theory holds up under some of the most extreme gravitational conditions in the universe.
So these bursts are essentially testing grounds for some of our most important scientific theories.
Precisely. And so far, Einstein's theory has passed every test with flying colors.
Yeah.
But each new observation gives us another chance to refine our understanding of gravity and its role in shaping the universe we see.
This is all so mind-blowing.
It is.
I'm so excited to learn more about the mysteries of the cosmos.
Well, I'm excited to share them with you.
And with our listeners.
Yeah, definitely. And with our listeners. Ready to dive back into the world of gamma-ray bursts. We left off talking about how these events are helping us test some of the most fundamental theories in physics.
I'm ready. But I'm also curious about some of the challenges scientists face in studying these bursts.
Yep.
What are some of the hurdles they have to overcome?
Well, one of the biggest challenges is that gamma-ray bursts are incredibly unpredictable.
What do you mean by unpredictable?
We can't predict when or where the next one will occur.
Oh.
They can happen at any time, in any direction, with absolutely no warning.
So it's like a cosmic guessing game.
In a way, yes.
Wow.
Our telescopes are constantly scanning the sky, hoping to catch the next burst as it happens.
Okay.
It requires a lot of patience and a bit of luck.
It sounds like astronomers have to be constantly on their toes, ready to spring into action at a moment's notice.
Exactly. When a burst is detected, it triggers a flurry of activity.
Oh, wow.
Teams around the world scramble to point their telescopes at the right patch of sky.
Right.
And they have to work quickly because those initial bursts are incredibly short-lived.
We talked about the afterglow earlier, but how long does the initial burst itself actually last?
It varies, but many are over in just a few seconds, some even less.
Wow.
By the time we detect them and get our telescopes pointed in the right direction, the most intense part of the show might already be over.
So it's like trying to understand a fireworks display by only seeing the fading smoke trails.
That's a great analogy.
Yeah,
We're missing crucial information about the very beginning of the burst, the moment when all that energy is first released.
right.
That's why scientists are always working on new technologies and strategies to try and catch these bursts earlier in their evolution.
It sounds like a race against time trying to capture these fleeting moments of cosmic fury.
It absolutely is.
Yeah.
And every millisecond counts if we want to understand the extreme physics at play in these events.
Okay, so unpredictability and the short duration of those initial bursts are two major challenges. Are
Right.
there any others?
Another big one is the difficulty in observing those incredibly faint gamma ray bursts.
Okay.
Not all bursts produce bright, easily observable afterglows.
Right.
Some are just too faint for our telescopes to pick up clearly.
So it's like trying to hear a whisper in a hurricane.
Exactly. Those fainter bursts are harder to study,
Yeah.
and we might be missing a whole population of them simply because they're too dim for our current instruments to detect.
It makes you wonder what other secrets the universe is hiding from us
Yeah,
just because we haven't developed the tools to see them yet.
absolutely.
Wow.
And even when we do detect a gamma ray burst, understanding the environment where it occurred is crucial.
Right.
We need more information about the galaxies where these bursts are happening, the types of stars involved, and the conditions surrounding them.
So it's not just about catching the burst itself, it's about understanding the context, the bigger picture.
Precisely. And that requires careful observation and analysis, piecing together the clues to understand the full story.
Now, we've talked about the observational challenges, but are there also theoretical hurdles that scientists are grappling with?
Definitely. One of the most perplexing theoretical puzzles is the origin of those ultra-long gamma ray bursts.
The ones that last for hours, right?
Yeah.
I remember you mentioning those earlier.
Yes.
It's hard to imagine what could possibly sustain such a burst for that long.
Exactly. It challenges our current understanding of stellar physics.
Wow.
We have some ideas, of course.
What are some of the leading theories?
One possibility is that they're linked to the collapse of supermassive stars, stars hundreds or even thousands of times more massive than our sun.
Right.
These hypothetical stars would be true behemoths,
Yeah.
and their deaths would release unimaginable amounts of energy.
It's mind-boggling to even think about stars that large.
It is, but there are other possibilities as well.
Okay.
Perhaps ultra-long bursts are the result of some kind of interaction between a black hole and the matter surrounding it.
So like a black hole feeding frenzy, but on a much grander scale?
Exactly. As a black hole devours matter, it can release tremendous amounts of energy.
Right.
And it's possible that this could power a burst lasting for hours.
It's like the black hole is a cosmic engine, driving these incredibly powerful events.
It's a fascinating possibility that researchers are actively exploring.
Yeah.
But for now, the true origin of ultra-long gamma ray bursts remains one of the biggest unsolved mysteries in astronomy.
It seems like there's still so much we don't know about these enigmatic bursts.
There is. But that's what makes studying them so exciting.
Yeah.
Every new discovery opens up new avenues of research, leading us deeper into the mysteries of the universe.
It's like we're piecing together a giant cosmic puzzle, and each gamma ray burst is another piece that helps us see the bigger picture.
That's a great way to think about it. And with each new piece, we get closer to understanding the fundamental laws of physics and the grand story of how our universe came to be.
This is all so inspiring.
It is.
It makes you realize how much there is still left to discover out there.
It does. And it highlights the importance of continued exploration and the ingenuity of the scientists who are working tirelessly to unravel these cosmic secrets.
I, for one, am eager to hear about the progress they make.
Yeah.
It seems like the future of gamma ray burst research is full of promise.
It absolutely is.
Okay.
We have a new generation of telescopes coming online both in space and on the ground that will allow us to observe these bursts in greater detail than ever before. We'll be able to capture those fleeting moments of cosmic fury with incredible precision.
So we'll be able to zoom in and see these events unfolding with even greater clarity.
Exactly. And with the continued development of multi-messenger astronomy,
Right.
we'll be able to combine observations of gamma rays with gravitational waves, neutrinos, and other signals.
Wow.
This will give us a truly holistic view of these cosmic events, allowing us to peel back the layers of mystery and see them in a whole new light.
It's like we're building a cosmic orchestra, and each new instrument we add brings us closer to hearing the full symphony of the universe.
That's a beautiful way to put it. And gamma ray bursts are playing a leading role in that symphony, guiding us toward a deeper understanding of the cosmos and our place within it.
Yeah.
But for now, let's take a quick break. When we come back, we'll explore some of the most exciting questions that still remain about gamma ray bursts and delve into the cutting-edge research that's pushing the boundaries of our knowledge about these incredible events.
Welcome back to Cosmos in a Pod. We've been on quite a journey exploring these incredible gamma-ray bursts.
We have, from those serendipitous early discoveries to the ongoing quest to understand their role in shaping the universe, it's been an amazing ride.
It really has, and I'm especially intrigued by those lingering mysteries we touched on earlier, the ones that keep astronomers up at night.
Oh, yeah.
Let's dive back into those, shall we?
Absolutely. Where would you like to start?
Well, those ultra-long gamma-ray bursts, the ones that last for hours,
Oh,
they really captured my imagination.
yeah.
What are the latest thoughts on what could possibly power such sustained bursts of energy?
It's a question that continues to puzzle scientists.
Yeah.
The energy scales involved are simply mind-boggling.
It seems like they defy our current understanding of how stars live and die.
They do challenge our existing models. One intriguing avenue of research involves the possibility of quasi-stars.
Quasi-stars, okay.
Imagine a massive early universe star with a black hole at its core.
Okay.
Instead of collapsing completely, the black hole keeps accreting matter from the star's outer layers, releasing tremendous amounts of energy in the process.
So it's like a star with a black hole heart, constantly feeding and fueling these incredible bursts.
That's the idea. These quasi-stars, if they exist, would be unlike anything we've observed before.
Right.
They could potentially explain those ultra-long bursts that have us scratching our heads.
Yeah, it's a fascinating concept. Are there any other theories being explored?
There are.
Okay.
Another line of thought involves the interaction between a black hole and a dense disk of gas and dust surrounding it.
Right.
As material falls into the black hole, it heats up and emits powerful radiation, potentially including gamma rays.
So like a cosmic whirlpool with a black hole at the center, swirling material around and generating those intense bursts of energy.
Exactly. And these systems could potentially produce bursts lasting for hours or even longer, depending on the amount of material available to fuel the process.
This is all so mind-blowing. It seems like every answer we uncover leads to even more questions.
That's the beauty of scientific exploration.
Yeah.
And speaking of questions, remember those incredible relativistic jets we talked about? The ones that shoot out from gamma ray bursts at nearly the speed of light?
Right.
Well, understanding how those jets form is another major challenge.
Right. We talked about them being like cosmic lasers, but how do they actually come about? How does a dying star or a pair of merging neutron stars manage to focus so much energy into those narrow beams?
It's a question that keeps theoretical astrophysicists busy.
Yeah.
One of the most promising areas of research involves the role of magnetic fields.
Okay.
Imagine the intense magnetic fields of a collapsing star, or those generated during a neutron-star merger.
Okay.
These fields could act like a cosmic nozzle, channeling the outflowing energy and matter into those focused jets.
So it's like a magnetic funnel, shaping and directing the flow of energy.
Exactly, but it's not just about magnetic fields.
Right.
The rapid rotation of those collapsing stars or merging neutron stars also likely plays a crucial role.
So it's a combination of those powerful magnetic fields and incredible rotational forces working together to create those awe-inspiring jets.
That's the current thinking. Of course, the details are incredibly complex and there's still much we don't understand. But scientists are developing sophisticated computer simulations to model these processes and get a clearer picture of how those jets form and evolve.
It's amazing to think that something as seemingly simple as a beam of light can hold so many mysteries.
It is. And it reminds us that even the most familiar phenomena can hide incredible complexity when we look closely enough.
And those complexities have implications beyond the bursts themselves, right?
Right.
We talked earlier about the impact gamma ray bursts can have on their surroundings, on the evolution of galaxies.
Exactly.
Oh.
Those bursts release immense amounts of energy, and that energy has to go somewhere. It can heat up gas in galaxies, influence star formation, and even spread heavy elements throughout the cosmos.
So these bursts aren't just isolated events, they're actively shaping the universe around them.
Precisely. One of the fascinating areas of research is studying how those bursts might have influenced the early universe.
What kind of influence are we talking about?
Well, in the early universe, galaxies were smaller and closer together.
Right.
A powerful gamma ray burst could have potentially swept through a neighboring galaxy, disrupting its gas clouds, influencing its evolution, even triggering or halting star formation.
So these bursts could have been instrumental in shaping the very structure of the early universe.
That's a possibility scientists are exploring.
Wow.
It highlights how these seemingly distant and fleeting events can have profound and lasting impacts on a cosmic scale.
It really underscores the interconnectedness of everything in the universe, doesn't it?
It does, and it makes you wonder, what other connections are we missing? What other secrets of the universe are waiting to be uncovered?
That's what keeps me coming back to astronomy.
Yeah,
There's always something new to discover, always another mystery to solve.
I couldn't agree more. And the future of gamma ray burst research is brighter than ever.
Yeah.
We have a new generation of telescopes coming online, like the James Webb Space Telescope and the upcoming Cherenkov Telescope Array, which will give us unprecedented views of these events.
So we'll be able to see those gamma ray bursts in even greater detail, capture those fleeting moments with even greater precision.
Exactly. And with the continued growth in multi-messenger astronomy, combining observations of gamma rays with gravitational waves, neutrinos, and other signals, we're entering a golden age of discovery.
Wow.
We're poised to unravel the remaining mysteries of these incredible cosmic beacons and gain an even deeper understanding of the universe we call home.
It's an exciting time to be an astronomer, that's for sure. And it's inspiring to think about all the incredible discoveries that
Yeah.
await us.
It is, and who knows what those discoveries will reveal. Perhaps they'll challenge our most cherished theories, or perhaps they'll open our eyes to entirely new phenomena we haven't even imagined yet.
Well, folks, that concludes our deep dive into the world of gamma ray bursts. We've covered a lot of ground from their accidental discovery to their potential role in shaping the universe.
We've explored their origins, their mechanics, the challenges of studying them, and the incredible insights they provide into the most extreme environments in the cosmos.
We hope you've enjoyed this journey as much as we have, and if you're hungry for more cosmic adventures, be sure to follow and subscribe to Cosmos in a Pod.
And don't forget to check out our YouTube channel for stunning visuals and animations that bring these cosmic events to life.
Until next time, keep looking up, keep wondering, and never stop exploring the wonders of the universe.
And keep listening to Cosmos in a Pod for more deep dives into the most fascinating corners of space and astronomy.